For these molar mass problems, what you need to do is you need to look at the formula of the compound. You need to look at the average atomic masses for each element in the compound and simply add them together. Looking at sodium, it has a mass of 22.99 grams per mole. Oxygen has an average mass of 16. Hydrogen has a mass of 1.01. So if you sum them all together, and just so you know, I round all these to 2 decimal places. The molar mass of sodium hydroxide is 40 grams, or you could say 40 grams per mole. Either one is acceptable. For this one, we have calcium phosphate. Okay, you'll notice there are 3 calciums present, so I have 3 times 40.08, which is the mass of calcium. Right, I have 2 phosphorus. Each phosphorus has a mass of 30.97. And then I have 8 oxygen. It's 16 each. 2 times 4 is 8, so 16 oxygen. If I sum all of those, I get 310.18, and you can say grams or grams per mole, either or. So 1 mole weighs 310.18 grams. In this example, we have magnesium sulfate and heptahydrate. And so what that means, this little symbol, normally in algebra you think that's multiplication, but here, because this is a hydrate, what this tells me is that these water molecules are trapped within the solid crystalline structure of magnesium sulfate. And so these are hydrated crystals, ones that have water incorporated in them. And so you do this much the same way as you did the others. You have to add up the individual masses. And so magnesium, I have 24.31 grams. Sulfur is 32.07. I have 4 oxygens, each at 16. And then notice I have 7 waters, and I know water from previous experience is 18.02 because you have 2 hydrogens at 1.01 and 1 oxygen at 16. And so if I multiply those and sum them all, you come up with the the molar mass, 246.52. You can say grams or grams per mole. Okay, we're going to start some conversions now. As always, you got to start with what you know. 0.431 moles of zinc sulfide. All right, so in looking at this, we're looking for mass. Well, I can tell you the mass of 1 mole, and so to get rid of the mole, I'm going to put 1 mole in the denominator. Anytime you have moles in mass, it's always 1 mole. And then I have to calculate the molar mass of zinc sulfide, so I add up the mass of 1 zinc and 1 sulfur, and I end up with 97.48. That's its molar mass, grams per mole. Moles cancel. I multiply 97.48 times 0.431. My answer, rounded to the appropriate number of sig figs, 42.0 grams. Don't forget to identify significant figures and also to put your unit labels. In this example, we're counting the number of atoms in 7.5 moles of sulfur. So 7.5 moles of sulfur, well, I know that in every 1 mole there are 6.02 times 10 to the 23rd atoms. Moles cancel. I take 7.5 times 6.02 EE 23, and my calculator is going to report with 2 sig figs 4.5 times 10 to the 24th atoms. In this example, we're calculating a mass to a number of moles. So once again, as always, start with what you know. 1.75 grams of sodium bromide. And so, let's see, I know that 1 mole, this time the mole is in the numerator because the mass is going to be in the denominator. If I add up the mass of sodium and bromine, I come up with 102.89 grams. Grams are going to cancel. I take 1.75 divided by 102.89. My calculator is going to report 0.0170084556 I'm limited to 3 sig figs because the only measurement has 3 significant figures. This answer is going to be 0.0170 moles. Do not forget that last 0 because that's the one that makes it 3 sig figs. The leading 2 zeros are non-significant. Okay, here's a problem where we're going from molecules to grams. There is no relationship between molecules and grams. You have to go through an intermediate step. That step is called the mole. As a little hint, anytime you're doing any of these conversions, you should have noticed that we use moles in every single problem. There isn't one that doesn't contain them. And so, let's look at this one. We're going to begin with what we know, 2.13 times 10 to the 24th molecules, and I'm going to abbreviate molecules with a C so we know it's not moles, of carbon dioxide. Well, I can convert molecules to moles knowing that there are 6.02 times 10 to the 23rd, Avogadro's number, molecules in 1 mole. Molecules cancel. I now know moles. Once I know moles, that's easy because I know the mass of 1 mole. 1 mole of carbon dioxide is going to be 44.01 grams. That's simply 1 carbon, 2 oxygens when you add them up. Moles cancel. I take 2.13 times 10 to the 24th times 44.01 divided by 6.02 times 10 to the 23rd, and this is going to give us 155.7164452 is what my calculator tells me. However, I'm limited to 3 sig figs because the measurement had 3. The answer rounded is going to be 156, the unit grams. Okay, to calculate mass percent of any compound, the formula is very easy. It's going to be the molar mass of the element divided by molar mass of the compound times 100. Simple, simple. And so if you have a problem where it's asking for the percent composition of each element, the nice thing is that you can kind of check your work because they should add up to 100 or really darn close. And so let's look at this example. I want to find the percent hydrogen in ammonium nitrate. So first off, let's see, there are 2 nitrogens, each at 14.01, plus, let's see, 4 hydrogens, each at 1.01, plus there are 3 oxygens, each with a mass of 16. And so if I multiply and then sum all these, I find the total mass of this compound weighs 80.06 grams per mole. And so I look at this, I take the mass of the element, so it's asking for hydrogen, and so I don't want to put 1.01 because there are 4 of them, so 4 times 1.01, we have 4.04 grams of hydrogen over the entire compound, which is 80.06 grams. Notice the grams cancel, times 100, so if I do the division, then multiply, my answer is going to be 5.05%. I really don't look at sig figs in these type of problems because there shouldn't be any error. The measurements that you're using, first off, this is counting, and there's no error in the number of atoms of each. Hopefully we can count to 4. And then the measurements that we took for the masses, those are taken from the periodic table, so those are accepted standard values. My suggestion would be that I would always go to at least the 10th, if not the 100th, when I'm doing percent. Okay, we have a very similar problem here, except for the difference is I don't have the formula. Calcium hydroxide, you know calcium's 2+, you know hydroxide is OH and 1-, so the formula for calcium hydroxide is CaOH parentheses 2, telling me there are 2 hydroxides to bond with that calcium. And so I'm going to do the same type of calculation. Calcium has a mass of 40.08 grams per mole. There are 2 oxygens, each at 16. And there are 2 hydrogens, each at 1.01. And so if I sum all those masses up, you get 74.1. And so I look at the mass of the oxygen. There are 2 of them times 16, so that gives me 32 grams per mole. The total mass is 74.1. The grams are going to cancel, times 100. 43.18%. Like I said, I would go out to probably 2 decimals. All right, this is an empirical formula problem. And so just remember, kind of that sing-songy, limericky rhyme is you're going to take percent to mass to moles, divide by the small, and round till whole. And so that, you're like, well, it doesn't have a lot of meaning. Well, let's run through it and see. Hey, you'll notice that the first thing we have are percents. So the nice thing is we can turn the percents into grams by just pretending we have 100 grams of the substance of this unknown. That makes our work a lot easier because 50.7% becomes 50.7 grams of carbon. Now I can convert those grams to moles knowing that 1 mole of carbon has a mass of 12.01 grams. Grams cancel, and so I multiply, this gets 4.22 moles of carbon. I'm going to do the same thing for the hydrogen. You can't see it, there's a decimal there in the problem, but 4.2 grams of hydrogen. Well, every 1 mole of hydrogen has a mass of 1.01 grams. Grams cancel. I have 4.16 moles of hydrogen. I do the same thing for the oxygen. 45.1 grams of oxygen. I know that for every 1 mole it weighs 16 grams. Grams cancel. And divide 45.1 by 16, you're going to get 2.82 moles of oxygen. Now that I know the number of moles of each, I want to take the smallest number and divide everything by it. Okay, the smallest one is going to be the 2.82. That's going to make this one 1. Divide by 2.82. Divide by 2.82. And when you do this, you're going to find out, these aren't exactly 1.5, but my goodness, they're really close. You got like 1.49 and 1.48, which is essentially 1.5, which is really 1.5. And so this tells me I have 1.5 moles of carbon, 1.5 moles of hydrogen, and 1 mole of oxygen. Well, guess what? You can't have a formula like this. You can't have C 1.5, H 1.5, O. It's just not cool. How do you get rid of a half? You double it. What's 1.5 doubled? C3, H3, and then 1 doubled is 2. This would be the empirical formula for the compound. Just recall, when you guys are doubling these, if you ever end up with a fraction, or excuse me, a decimal that's like 0.25 or 0.75, that correlates to a quarter or 3/4. How do you get rid of those? Multiply by 4. If you get a decimal that ends with like 0.33 or 0.66, these correlate to 1/3 or 2/3. How do you get rid of them? Multiply by 3. And then as we just saw, if you have 0.5, how do you get rid of that? You double it. You get rid of halves by doubling. Those would be the common ones. And they're not going to come out to be necessarily exact every time, but they'll be really close. This is a very similar problem. The only difference is that I was given the mass to start with. Actually, I was only given the mass of phosphorus. I do not know the mass of oxygen, but that's easily solved because I know that I have a total of 1 gram of the sample. And if I subtract the 0.437 grams of phosphorus from it, I find I have a remainder of 0.563 grams of oxygen. Now, I know you might be thinking, oh, I should round that to the proper number of sig figs because 1.00 only goes to the 100th place. Should I just call this 0.56 grams of oxygen? I wouldn't. The reason being, sig figs aren't going to matter in the end of this problem anyway because we're writing an empirical formula. It's going to be a whole number ratio. And the more numbers we have, early on, the easier it's going to make it in the end to round it to the correct number of atoms, really. And so let's take a look at this. Let's start with what we started with, 0.437 grams of phosphorus. Let's convert this to moles. Well, I know that for every 1 mole of phosphorus, it has a mass of 30.97 grams. Grams cancel. I divide, and I'm going to end up with 0.0141 moles of phosphorus. And then I'm going to do our calculated amount of oxygen, 0.563 grams of oxygen. Well, for every 1 mole of oxygen, it weighs 16 grams. Grams cancel. 0.563 divided by 16, it's going to give me 0.0352 moles of oxygen. And so now that we know the mole ratio, we're going to divide each by the smallest number, which is 0.0141, 0.0141. This one comes out to be 1, and this comes out to be 2.5. Okay, so you cannot have PO 2.5. How do you get rid of the 2.5? Easy, you've got to double it again. So P, which is 1, becomes P2, and then O becomes 5.